more dense object. So instead of spinning this way, like that top picture, it's spinning like this. So the idea is that the moon, or the smaller object here, is in a greater motion and the Earth is in a smaller motion. Of course, 4:1 is not actually what the ratio is. Let me just take this one step further. Let's assume that we have an object that's really massive, 16 times the mass of the other. So now the actual spin of the larger object, it's basically a wobble, because the point around with which both of these objects spin is now inside of the diameter of the planet. Okay, it's not in the middle, but it's offset to some degree. Okay, so this is just a visual demonstration, and you can do this with, you know, a shell and your blow up Earth, for example. I've done this actually. The ratio of that difference is actually 82:1. So the Earth is essentially 82 times the mass of the moon. And so what that means is it's not just the moon circling around the Earth. The Earth is also doing a circle. It's just doing it around a point that's inside the diameter of the Earth. So the Earth, the effect, if you were just looking at the Earth, is this. It's actually wobbling as the effect of the moon going around the Earth. Okay, this is critical because this explains why there are two bulges around the planet. This is a nice little demonstration of it. This red line actually shows the axis around which both the Earth and the moon are spinning as a result of the gravity of the two of them pulling against each other. It's not just that the moon is pulling against us, we are pulling against the moon. And so this shows why there's a little bit of a wobble in the Earth. So this line here down the middle is the center axis. That's where the Earth is spinning. But this red line here is showing the point around which the Earth and the moon are collectively moving with respect to each other. So what that means is, because of this, you have gravity pulling on one side, but you have literally a flinging effect, almost like centripetal force, if you will, forcing water out on the other side in an equal way. So they're essentially equal. So this explains why there are two high tides in a day and not just one. Okay, so hopefully that helps. Now, I've mentioned the moon, and the moon certainly does have an effect, but the sun also has an effect, but it's 400 times further away. And due to stuff that Isaac Newton came up with, therefore, because it's so much further away, it doesn't have as great an effect. However, it still does have a measurable effect. And so with the moon and the sun, with their gravitational effect on the Earth, and the fact that water is responding to all of this, there are going to be times in the day when they are complementary, or I should say times in the month when they're complementary, and times when they're not, when they kind of cancel each other out, although the moon still has a greater effect than the sun. So when the moon and the sun are in alignment with the Earth, we refer to that actually as a spring tide. And I'm going to show you some pictures here in a second. And that's because the moon and the sun being in alignment have a greater impact in essentially misshaping that water bulge to a greater degree. And so there's two ways that you can see this, where the moon and the sun are on the same side, and then also where the moon and the sun are on the opposite side. Either way, it doesn't matter. They still have that complementary effect. So during a neap tide, though, that is where the moon and the sun are at right angles to the Earth. And so again, that can happen in two ways too, with the moon on one side versus on the other side. And so here they are not complementing each other. They're actually canceling each other to some degree. And so in all four of these pictures, these are things that occur over the cycle of a month. And if you know how long it takes for the moon to get once around the planet, it's about 28 days, roughly about 28 days. But in that time, Earth has spun underneath that 28 times, right? So we spin in a single day, but it takes us 28 of those in order for the moon to make one circle around us. This is what makes the tides a little bit complicated. So when you're looking up at the sky, this is how you will know that you are in a spring tide. At night, it's pretty easy. If you have a new moon or a full moon, then you know that you are going to be experiencing the spring tides, because the only way to have the moon look this way is if it is in alignment with the sun. The sun is either shining entirely on the surface, which means that they are literally right on opposite sides of the earth, or that it's actually blocked, and the part that's being lit up by the sun, you can't see. It's on the backside to us. So we experience these as very high tides and very low tides. And this occurs roughly every 2 weeks. Now, if the moon is in that intermediate phase where you're seeing half of it, and we refer to this actually as a first and third quarter moon for reasons that I don't understand. First and third? Well, I guess I kind of understand that. When they are at right angles to each other, you're essentially seeing the sun shining on only half of the moon visible to your eyes. And again, because they are at right angles and not complementing each other, your tidal range, your highest highs and your lowest lows, are actually much more dampened. Okay, now here's one of the problems, though, is that in Southern California, we have 2 high tides and 2 low tides, but they're not equal. One high tide is much higher than the other high tide in a 24-hour period of time. And this is a question I get a lot from people in the public. What makes it different? Well, it has to do with this. When you are demonstrating this to your audience, and you have your Earth and your moon is kind of spinning around it like this, keep in mind that that bulge, which should be facing the moon, is occurring on a planet that is actually tilted and spinning at an angle. So it's about a 23-degree angle, thereabouts, which means that when the moon is over here, the tidal bulge is actually traveling at a diagonal to the planet. And so when you have a tidal bulge that's extended out this way, and it's actually on a tilted planet, as the planet spins, you're going to experience high tide. It's kind of like having a bulge like this. You're experiencing high tide here at one point, and then high tide down here at the side of your bulge at another point. And so that's what makes them at slightly different heights. And so this here is the tides from today down at Newport Beach Pier, where you have 2 high tides and 2 low tides because of this tilt that is occurring on planet Earth as it spins with the moon kind of up above us. So here's another complication to this too. So we explained it this way, and that makes perfect sense in a water world situation. But the reality is we have continents in the way, and continents don't move. Water moves, but continents don't, not in this time scale. And so when water is moving in response to the moon and the sun, it has to do so around these fixed positions, these fixed continents. And what this does is it sets up a complex movement of flow patterns that makes it a little bit more difficult, a little bit more of a challenge to predict. And by the way, because of this, because we force water to move around coastlines that aren't even straight, oftentimes there's curvature to it, and we have inland areas, we have embayments, we have entrapped waterways. The tides affect all of that. If it's water, it's being affected by our tides. And given that our coastline is not perfectly straight, it is the reason why, as we force water around the globe because of where the moon is and the sun is above us, it means that when the highest high tides are experienced, are going to be slightly different along the coastline. So I picked this, by the way. This is these are the tides for today for Cabrillo Beach up near the Port of Los Angeles and down at Imperial Beach. And I chose these 2 points because they're basically a little more than 100 miles away. That's only 100 miles. On the grand scheme of things, you would expect them to still be at the same time, and yet they're not. They're actually offset by about 6 minutes. And it's due to the fact that water is rushing and actually being forced around fixed continents, that they occur at slightly different times. So there's more to this also. The fact is that the effect of the moon and the sun is changing every single day. And whereas we have our moon here and our Earth here, in the period of time that the Earth has spun one time around, the position of the moon has actually moved 1/128th in the sky, which means it shifts when the tides are going to be tomorrow by about 50 minutes. So if you want to know what the high tide is going to be tomorrow, just pick today's time and add 50 minutes to it, and you're going to be pretty darn close. Anyway, and then of course, we're all out there to enjoy the animals too, especially at low tide. And so it's good to talk about the impact that these tides have on animals that have evolved to live in seawater. And yet there's going to be periods of time when they're going to be exposed to the air. And that's a huge challenge. So that's, of course, a different talking about life living, or what it means to live in a variable environment like this, where you're covered by seawater half the time and not the other half. And so the tides having occurred forever on planet Earth, these living animals have evolved life histories that tie to this entirely. So if you want to know more about this, I actually do have a video which I will provide, which goes into much greater detail on the things that I just presented in the last 15 minutes. 15 minutes is certainly not enough time to become an expert on the tides, but hopefully I piqued your interest in wanting to know more. So thank you very much, and I'll answer any questions.
Thanks, Kimo. There is one question. Don is asking, is the water also gravitationally affected by the moon and sun?
Yes, it absolutely is. Again, it has to do with the fact that water is fluid, and it basically moves in response to gravitation in ways that rocks don't. And by the way, because water's a fluid, it's not the only fluid that's affected by our tides. Believe it or not, there are actually tides associated with our air mass. So our atmosphere actually has tidal effects as well. We just don't see it.
Thank you so much, Dr. Morris. We really appreciate that. I'm already getting text messages on my phone that they're inspired and learned something new, even if they felt like they knew how the tides worked. So thank you very much for presenting. We're definitely going to keep this YouTube link. It is going to be shared with all of you today because it is a really interesting watch, and you get to learn a little bit more in depth than what you had to abbreviate for such a short presentation. So thank you for coming to speak to us and dumbing down tides in 15 minutes. We really appreciate it.
Thank you.
Thank you.